Okay, the main thrust here is how we can use matrices and matrix calculations for the sane and demented problem. There's a little preliminary thing that I'll just say, that this is what you do when you have your depth versus clock time for water flowing from a uniform cylinder from a uniform hole in the side of the cylinder. You graph the depth versus clock time, you fit a smooth curve to your data trend, sketch your tangent lines at 4 equal time intervals, estimate the slopes of the tangent line, and graph slope versus t, which constitutes constructing a slope graph. So that's kind of worth knowing, but that's not the main idea here. Okay, so we want to go to the sane demented problem. And the basic problem is you have 500 sane people, 500 demented people, and 10% of your sane people become demented during any time period, month, week, day, whatever, during some uniform time period, and 20% of your demented become sane. Now ignore the writing in purple. It has nothing directly to do with what we have here. I had to insert that and kind of append it, and we'll get to it at the very end, but it's not relevant right now. Okay, well, this is a problem that nobody has any problem doing. 10% of the sane become demented. 10% of 500 is 50, so 50 sane people become demented. And 20% of the demented become sane. 20% of the 500 demented is 100 of the demented become sane. So you end up with 550 sane and 450 demented. Now there's a more efficient way to calculate this sort of thing. We can see that if 10% of your sane become demented, then 90% of your sane are going to remain sane. So if S stands for the number of sane people and D for the number of demented people, 0.9S stands for the 90% of the originally sane people that stay sane. And then 0.2D, that's 20% of your number demented. It's the number of demented that become sane. So 90% of our sane people are still sane. 20% of our demented people become sane, meaning that our new number of sane, which I denote by S prime, is 0.9S plus 0.2D. Similarly, the new number of demented. Well, what happens if we have a certain number of sane and demented? How many will we have that are demented? Well, 10% of your sane will be demented. And since 20% of your demented become sane, that leaves 80% of your demented who are still demented. So that the new number of demented is 0.1S plus 0.8D. Now, we move up here. I had to find my place in the board. I hadn't looked up high enough. I'm going to say that this 0.9S plus 0.2D, the new number of sane, S prime, can be written this way, where 0.9, 0.2 is what we call a row. We call it a row vector, if you like. And SD, your populations of sane and demented, is in a column, and we call that a column vector or a column matrix. We call this a row vector or a row matrix. Okay? The rule for multiplying a row by a column is you take the first number in the row and multiply it by the first number in the column. You take the second number of the row and multiply it by the second number in the column. Now, there might be more numbers in the rows and columns. As long as the number in as long as you have an equal number of numbers in the row and column, you can match them up and multiply them. So, first number in the row by the first number of the column, second number of the row by the second number of the column, and so on until you get to the end of the column and the row. And then you take those numbers and add them. So in this case, you do 0.9 times S and 0.2 times D and add them. Well, that's exactly what you have over here. So that this rule for multiplying a row by a column with that row and that column gives us exactly this. Okay, and then the D prime. And you should stop for a minute and write out how you would express this as a row times a column without looking at what I did. Hopefully you did that. And you see that the D prime is going to be 0.1, 0.8 row times the SD column, so that you end up with 0.1 times S plus 0.8 times D, which is what you need to have in order to give you D prime. So here you get it. Okay? Now, some people wrote that out this way. Okay? And that is correct. 0.8 times D plus 0.1 times S is 0.8 D plus 0.1 S, just in reverse order. So there's nothing wrong if you wrote it this way, except now that we really want to write it this way, so we write the S and D in the same order so that we can put all this into one expression with just SD here. Okay, if we got SD here and SD here, we put SD here, and then we write this row here, and we write this row down here. Now what this means is you multiply the first row by SD, and you get S prime. You multiply the second row by SD, you get D prime. Nothing too mysterious about that. Okay, well now I say that we want to use this to find SD if SD equals 800, 200, and that's S prime D prime. I didn't see the prime up here and didn't really notice it down there, so I didn't read it correctly. But this is S prime, find S prime D prime. That's the number after the transition if the SD column vector is 800, 200. Okay, so how do we do that? Well, we just put 800 here or 200 here and write this out. We're going to have 0.9, 0.2, 0.1, 0.8, this matrix, because we call this a matrix now when we have more than one row, multiplied by our, okay, I'm in the wrong place. This comes from here. I do it down here, I'm sorry. So we, again, put the 800, 200 in for SD. We have the 800, 200 multiplied by the 0.9, 0.2, 0.1, 0.8 matrix. And now what's our rule for multiplying by this matrix? Well, multiply 0.9, 0.2, 0.9 times 800, 0.2 times 200. 0.9 times 800, 720. 0.2 times 200 is 40. Add those up, we get 760. So there it is. Then our D prime, and of course that's our S prime. That's our first number. Second number is going to be our D prime. 0.1 times 800 is 80. 0.8 times 200 is 160. 80 and 160 is 240, and that's what we get. Now you could come back here and do the same thing we did here with the 500 population. With the, if there were 800 sane and 200 demented, you could figure this out, and you would get these numbers. Okay, this is a more compact way of writing it, but there's even more to it. This is really extremely powerful. Okay, now I'm going to talk a little bit about the power of it, and then we'll see what this orange and what this calculation and what this calculation all give us. We'll do that in a subsequent video.